Uh, we're going to continue with our discussion about power semiconductor devices today. Basically, the arrangement of this course is a very traditional one. We always follow the traditional way of learning. We started always from devices, similar to the course you have learned before, similar to the course of analog electronics. You always started from the operation principle of the basic devices. Well, this is good. We have to do this like this, because if you don't know some basic concepts in the device operation, then it is probably very hard for you to understand the operation of the circuit in the future. But on the other hand, this is also having a bad side and not so good. The bad side is the students will feel we spend too much time discussing a lot of difficult things, because basically the physics of operation of all these devices is really quite difficult for the students to understand. Okay, so usually what I would like to do is we do a little bit about the devices. We just discuss some of the basic concepts, and we'll leave part of the material in this chapter, in chapter 2, about the devices. We leave part of that material to the end of this course. We come back when we almost complete all the discussion about power converters, all different power converter circuits. We come back to the devices and review. And at that time, you probably have a better understanding already about some basic concepts, even about power electronic circuits, about power converters. And at that time, when you return to chapter 2, to the device, you probably will have a better understanding of what we put in there in chapter 2. So the first few classes might be not so interesting for you. It's always a lot of physics, so maybe not very interesting, but it's going to be over very soon. We'll have class today. Today's class will be discussing about one major device, a thyristor, and then the class on next Tuesday will be the next class. We'll have one more class next Tuesday, and that's the end of discussion about chapter 2. We'll stop there, and we will enter into the power converters. We'll start discuss power converters. And then in the end, I'll come back to chapter 2 again. And maybe at that time you will have a better understanding of the material. Okay, that's my plan. So we'll have class today and next Tuesday's class discussing about power semiconductor devices. All right, let's get into the the second major device we are going to discuss. Thyristor. As already told you before, the Chinese name thyristor, of thyristors. And before it was also called SCR, another name, silicon controlled rectifier. And then we also have a Chinese translation to that name. And also, I believe this is also a very good translation. Silicon controlled rectifier. But now, the Chinese terminology standard takes this translation. That's the translation or terminology we usually use in Chinese, thyristor. The history of thyristor, I was mentioning that it was invented in the late 1950s. And there are several years I put there describing different events in the late 1950s. But the most commonly accepted saying is that this was accepted by most of the people that thyristor was actually invented in 1957. This was the time when the first thyristor product appeared. And it was invented by GE. I know most of you already know that name. General Electric, I'm sorry. That's a very big international company in a lot of areas, but especially in the electric power engineering, and it's one of the major international companies in this area. And then after the invention of thyristor, the previously used vacuum devices, as we already mentioned before, became obsolete because thyristor has much better performance than the previous vacuum tube devices. If you look at the almost every aspect, the volume, the size, the weight, and the controllability, everything in every aspect, thyristor is much better than the vacuum tube device. They're still in use today. Thyristors are still in use today in many applications, especially in a very high power situation. Where's my mouse? Okay, here. Very high power situation. Very high power, how high is very high? Well, that's the question. Usually, when we talk about very high power, we're usually talking about power range up to, let's see, 5 megawatts and above, larger than 5 megawatts. Very high power. So usually you can see thyristors still in use in, let's say, 10 megawatts or 20 megawatts, even larger than that, 50 megawatts motor drive. Motor drive system, very large motor drive system. Okay, that's the first typical application. And thyristors are also used in HVDC, the traditional HVDC system, high voltage DC transmission system. Okay, in those areas, very high power, very high power application area. So the reason is that thyristor is still having the highest power handling capability. Among all the power semiconductor devices, thyristor is still the best one. It can handle the largest power. Okay, that's the reason. Let's look at the different aspects we're going to talk about. Appearance. If you look at the appearance, it looks similar to diode. If you compare, let's see, if you go back to which page? The appearance of diode. Which page is that? 14? Okay, good. If you look at page 14, there's the packaging of the thyristor looks similar to diode. You can see the only difference, there's only one difference. The difference here, we have an additional terminal, this one. Okay. Thyristor has an additional terminal. And similar to this one, this type of packaging, we have additional terminal like this. Okay. Otherwise, it looks similar to a diode. This additional terminal is called gate terminal. Okay, and the other two terminals, terminal A and K, these are the same. These names are the same as diode. A means anode. K means cathode. Okay? Well, that's the appearance. And as we mentioned before, when you apply a power semiconductor device into the circuit, then among all these three terminals, there will be two terminals that allow current flow, the high current flow through. That is A and K. The current will be flowing, the high current, large current will be flowing through A and K. Those are the two terminals for current, large current flow through. And then there will also be two terminals to connect to control circuit, because control circuit is going to send signals to control this device. Those are the two terminals for control signals is G and K. So you apply, when you want to control thyristors, you apply this signal across G and K. So K, terminal K, is the common terminal we mentioned before, because terminal K is used both for main circuit and also for control circuit. The symbol of a thyristor is also similar to diode. Also, there is only one difference. The difference here. You have an additional, this is really hard for me to figure out. Where is my mouse? All right. This is the only difference. Other than that, everything is the same as diode. You have terminal A and terminal K, okay? And then you have terminal G, gate terminal. Gate terminal, pay attention to this position when you draw this symbol. According to the standard, this terminal G, when you draw this terminal, the position of G is always put on the right-hand side when you follow the current flow direction. Current is always, when this thyristor is conducting, the current is always flowing from A to K. Therefore, when you flow from A to K, G, terminal G is on the right-hand side. If you put it on the left-hand side, that's wrong. Okay? Pay attention to the position of terminal G. The structure, the inner structure of a thyristor is actually different from diode. The inner structure is different. Although the outside looks similar to diode, but the inner structure is different. The inner structure, remember for diode structure is always, for power diode, it is a 3-layer structure. You have a P layer, you have N layer, that's the original p-n junction. But for power diode, you have a N minus layer, right? This N minus layer is used to handle high voltage. N minus is similar to intrinsic. That's for diode. That's the structure of power diode. Okay. For thyristor, this is a 4-layer system. This is different from power diode. You have 4 layers. Okay. You have P layer, N layer, another P, another N. So totally 4 layers. That's the inner structure. It is a 4-layer structure for thyristor. And the 3 terminals are connected in this way. Okay. These are the 3 terminals. Okay. And the terminal connecting to P1 layer is called terminal A. The one connecting to N2 layer is called terminal K. And then this terminal connecting to P2 is called terminal G. So this is the 4-layer structure for thyristor. Not so complicated. PN, 4 layers. And then if you want to discuss about the operation of this 4-layer device, about the operation of this thyristor, the typical way is to discuss based on discuss that based on equivalent circuit. Equivalent circuit. Actually, this is not so difficult. If we consider this four-layer structure in this way, we can look at this in another way. Then you can probably understand this equivalent circuit very well. Okay, let's see, this is P. This layer is called N1. This is called P2. Let me label this on both sides. If I consider this four-layer structure in this way, if I can cut this layer, this center two layers in this way, I cut it into two parts. Each layer is cut into two parts. And then I split these two parts a little bit. And I'm using a wire. Okay. Let's see, split these two parts, therefore it would be looking like this. Okay. And then I'm using a wire, conductor wire, to connect these two parts. Another wire, conductor wire to connect these two parts. That will be the same. I actually did not change anything. This structure is still the same. I still have P1, N1, P2, N2, four layers. But the difference is if I'm looking at this structure in this way, that's the same as what we showed there in that picture. If I'm looking at this structure in this way, then you can, let's see, this is a better picture here on the screen here. Okay. You can actually look at this thyristor as the connection of two three-layer devices. Okay. This actually is made up of two devices, and each of these two devices is a three-layer device. Okay, and the upper one has three-layer P1, N1, P2. That's three-layer, and the lower one is N1, P2, N2. So you have two three-layer devices. What is these two three-layer devices? You have PNP, you have NPN. That's looks similar to you. That's what? Transistor. That's transistor. So a thyristor, if you look at this inner structure in this way, then it can be considered as the connection of two transistors. The upper one is a PNP transistor. That's why I'm using this symbol as PNP transistor, electric symbol. And then the lower one is an NPN transistor. And these two transistors are connected in this way. Before we discuss about that let me tell you the three terminals, the names of the three terminals of transistor. For the transistor, we have, probably you started from the Chinese name, right? That's base in English. Okay, you have Okay, that's emitter. Okay, then the third terminal, collector. And that's usually the reason why we use this character B to represent base, E to represent emitter, and C to represent collector. Okay, those are the three terminals for transistor, and the connection of these two transistors inside a thyristor is in this way. The base terminal of this PNP transistor, the upper PNP transistor, is connected to the collector of the lower transistor, NPN. Okay? The collector of this PNP transistor is connecting to the base of this NPN transistor. That's the connection. Okay? So that's not very hard to understand based on the equivalent circuit. And based on the equivalent circuit, we can discuss about the operation. Physics of operation. This is a little bit difficult, but still you can quickly understand. Remember, the gate terminal is connected in the upper picture. In the previous picture, gate terminal is connected to P2 layer. Okay. P2 layer. And remember, this P2 layer is the collector of the upper transistor V1, and it is also the base of the lower collector V2. I'm using these two, V1, V2, to represent these two transistors. So G is connecting to the collector, and the collector of upper transistor and the base of the lower transistor. Okay. Terminal A is connecting to the emitter of upper transistor, and terminal K is connecting to the emitter of the lower transistor. Okay. Now, let's see how this thyristor is working. How this thyristor is working. If we apply from outside, okay, here, a positive voltage, I'm applying positive voltage to terminal A and negative voltage to terminal K. That's from outside circuit. I can do that. And then, in order to control this thyristor, I also need to apply some control signal between terminal G and K. Okay? So I'm using another, let's say, voltage source applying to terminal G and K. If I don't apply, let's see, when the switch is open, when the switch is open, there's no signal applied to G. Then what happens? Nothing would happen. Right? You do not apply any signal to G, then these two transistors is connected in this way. Even when you apply a positive voltage to terminal A and negative voltage to terminal K, nothing would happen because those two transistors are not turned on. No signals are injected, no currents are injected into the base of these two transistors. So there will be no current flow. Okay, that's what happened. But if we close this switch at this time, if we close this switch, close this switch, then you will inject current. You will generate current from this circuit, from this voltage source, and inject current into the base terminal of V2. V2 will have some base current. When V2 has some base current, what happens? V2 will be generating current flowing through okay. When you have base current for the transistor V2, there will be current flowing this way. And when you have current flowing this way, remember the collector of V2 is also the base of V1. So you will generate base current for V1 also. And therefore, when V1 has base current, V1 will also allow current flow through. Okay, from the emitter to the collector. Okay, when you generate this current, remember this current is also injecting into the base of V2. So that current is also generating additional base current for V2. That will make V2 to generate even large collector and emitter current. And therefore, the current flowing through here is even larger, and therefore the base current for V1 is getting even larger, and therefore the emitter and the collector current for V1 is getting larger, even larger. And that even larger collector and emitter current for V1 will be introduced into an even larger base current for V2. That is what we call positive feedback. That's what we call positive feedback effect. Okay, you inject a gate current that will cause V2. For V2, you have emitter current or collector current getting larger. When therefore, let me use IC2 to represent the collector current. And when that is getting larger, that will introduce to the even larger base current for B1. Okay? When B1 getting larger, you get larger collector current for V1. Okay? When V1 has a larger collector current, and that collector current is also the base current for I2. So IB2 is getting larger, and therefore comes back. When you have larger base current for V2, you get larger current for IC2. So that's positive feedback. And therefore, in this case, under this situation, even if I open the switch in the gate, I'm no longer injecting current to the gate anymore. At this time, even I open the switch, there will be still current flowing. There will be still current flowing in V1, generating IC1, and that IC1 will be acting as the base current for V2. And then there will be still current flowing. Okay, that's what happened. So therefore, when we inject under the positive voltage between A and K, when we inject gate current to thyristor, this thyristor will be having very large current flow through. Therefore, just like between A and K, you have very large current and the voltage is very small. Remember, for these two transistors, when you have very large collector or emitter current, you are driving these two transistors into saturation. Into saturation area. In the saturation area, the current flowing through the transistor is very large, but the voltage is very small. Saturation voltage is very small. So both these two transistors will be driven to saturation area, and you can allow very large current flow through, but the voltage is very small. So just like in a switch, turn on. Just like in a switch, turn on. Okay? That's the operation, physics of operation when you turn on the thyristors. And I also mentioned at this time, when you already turn on the thyristor, even if you take out this gate current, this thyristor will still be allowing large current flowing through, because the inner side has already established positive feedback. Thyristor will still be conducting. So in this case, we do not need this gate current anymore. So this is called this turning on controlling mode of sending an injecting current into the gate, and it is not necessary for you to continuously inject that gate current, and this thyristor will still be kept on. This controlling mode is called trigger. This is called trigger. Trigger means, if you look at the waveform of the gate current, you inject into the thyristor. If you want to turn it on, you inject some gate current here, and then when it's already turned on, you can remove it. This gate current can be decreased to 0. And the switch during this time, it was still kept on. It is always, after the triggering, it will stay in under on state. This is called trigger. Okay? That's the operation. Now, let me ask you a question. How do we turn it off? Through the gate. Do you have any idea? How can we turn it off? Can you guess?
Remove the voltage source applied on A and K.
apply to A and K, you remove the voltage source applied to A and K. Good, that is one answer. Remove the voltage, positive voltage. You were applying positive voltage between A and K. Between A and K. Okay, you now remove that. You just remove that. Remove that voltage, then it probably will be turned off. Any other solutions? Based on the operation. Somebody said, well, let's just remove the gate current. But that won't work. Because I said, when it is turned on, even if you remove the gate current, this device will still be kept on. So removing the gate current does not turn off the thyristor. Then, any other suggestion you have? Looks like there's no better solution there. This is probably the only way. From the outside circuit, let's say we either remove the voltage applied to A and K, or you can increase the resistor, increase that outside resistor here. Increase that resistor, therefore the current flow through the thyristor will be gradually decreased. Okay. When the current flowing through the thyristor is decreased to zero, then everything come back to the zero state. Okay. Thyristor will be turned off. Looks like that's the only possible way to have thyristor turn off. Okay. So it cannot be turned off by control signal. The only way to turn it off is through the outside circuit to decrease the current flowing through thyristor to zero. When the current flowing through thyristor is decreased to zero, then it is turned off. And if you want to turn it on again, you have to inject gate current again. Okay, so looks like that's the only possible solution. And remember, that's true. Okay, that's why a thyristor is called half controllable. Why is it called half controllable? Or half controlled device. Because through the gate terminal we can turn it on, but we cannot turn it off. We cannot turn it off through gate terminal. But actually there is, if you think about further about this question, or you look at this equivalent circuit for more time, you probably can generate another idea to turn off the thyristor. You have any other idea? Okay, we have already discussed about this side. Yes, you have an answer to that?
You would the different direction current.
Okay. If you can generate an IG in a different direction, originally we were always talking about inject current in this way to turn it on. And we said even if you remove that, you cannot turn it off. But what happens if we generate a negative IG? Negative Okay? We still have that possibility. If we inject a negative current into the gate, that will give us a possibility to, let's see, to drive V2 from saturation area back to the off state. When it is, as I said, when it is turned on, this transistor is on the saturation. Where is that saturation? Okay, it is in the saturation region. And if we can inject reverse current to the base of V2, then it might be drive that back to the off state or off state area. That means turn that transistor off. Turn off that transistor. So that is one possibility. Okay? That is actually this second proposal is actually the operation principle of a new device, another device. Gate turn off thyristor. Okay, we will talk about it in the later time. Gate turn off. That means we can, through the gate, we can turn it on. This thyristor, we can turn it on. We can also turn it off. So gate turn off thyristor is a fully controlled device. That's what we are going to discuss in a later time. But forget about this right now. For thyristor, if it is a thyristor, then it can be turned on through the gate, but cannot be turned off through the gate. Usually, there is another way of explaining the operation, physics of operation for thyristor. That is still based on this two transistors model, equivalent circuit. But you can have some detailed discussion based on those equations. If you still remember, for transistor V1 and V2, we can write out an equation like this. For V1, you have equation 1, 2-1. For V2, transistor V2, you have this equation. The collector current is always equal to alpha multiplied by the emitter current, IA. Actually, another, I would say, IA is equal to IC1. I'm sorry, IE1. The emitter current of V1. Okay, IK is the emitter current of V2. So for every transistor, according to what you have learned before, you always have this equation. The base current, the collector current is always equal to alpha multiplied by the emitter current and plus and the leakage current. This is usually very small. This current is usually very small. Collector current is always equal to alpha multiplied by IE. Alpha is what we call transfer coefficient. Okay? I'm not sure whether you still remember. Collector current can always be written as alpha multiplied by emitter current. And usually this alpha is smaller than 1, usually. And that's why collector current is always smaller than emitter current. Okay? So for both these two transistors, we can write out those two equations. And then based on those two equations, and based on the next two equations, you always have the next two, equation 3 and equation 4. IK is equal to IA plus IG. And IA is equal to IC1 plus IC2. Why is this? Why are these two equations existing?